I'm going to continue on with our understanding of an action potential by taking us through something called an action potential graph. Now, this should hopefully look somewhat familiar to you because in the muscle unit, this kind of correlates with the myogram. So in a myogram, you could plot out a muscle twitch, and you can see the point at which the muscle starts to contract and when the muscle starts to relax. And it all has to do with nervous impulses, and because of that, we can also plot out an action potential. So let's take a look at this action potential graph here. And you're going to use a tool called an oscilloscope. And basically, it's recording the amount of electrical impulse going through these leads as an action potential goes on. So as you can see, we have two axes here, right? Down here we have time, which is going to be in milliseconds, and that just want to make sure we all understand that this is milliseconds, not seconds. So this happens very, very quickly. And then on the vertical axis, we have membrane potential in millivolts. So this is the amount of voltage that is occurring between the inside and the outside of the membrane. That's that potential that we're talking about. So as you can see, this ranges from negative 65 millivolts up to positive 40. You know, every textbook's a little bit different. I told you negative 70 and plus 30. The reason why there's not a set number is because it's not a set number. It's an average. Everybody's a little bit different. Every neuron is a little different. It's in a range. But I'm going to stick with my negative 70, positive 30, because that seems to be the common accepted value. But as you can see here, it's a negative 65 and plus 40. So it depends on the textbook. But let's take a look here. So at negative 65, what's happening is we're at what's considered it's polarized, right? And it's polarized because it's negative 65 on the inside and it's 0 on the outside, and that is considered resting potential. And again, just to clarify, that is maintained by several different factors. One is that there's more sodium outside than inside. There are those potassium leakage channels. There's those large negatively charged proteins on the inside. And then finally, there's the sodium-potassium pump that pulls 2 potassiums back into the cell for every 3 that it kicks out. And that keeps that imbalance of charge. So that's going to be our resting potential. And then there's something that occurs. This neuron is going to get stimulated, and that leads to depolarization. So as you can see, this difference in charge changes drastically, and it goes from negative 65 all the way up to positive 30. And that is called depolarization. And that occurs because the sodium channels open and sodium floods in. Again, this whole process is all about timing of those channels opening and closing. So the sodium channels open, and then that slower deactivation gate closes. So this whole thing happens very quickly, but the sodium channel opens, and the activation gate opens, sodium starts to flood in, and that slower inactivation gate finally closes, and that limits the amount of sodium that can come in, and that is why this spikes up to positive 30, but then it stops at a certain point. The reason why it stops is because that inner door, that inactivation gate closes, and at this point the potassium channels open, and when the potassium channels open, potassium floods in, and that is going to be called repolarization, and it's repolarization because it's going back down to a negative. And then it eventually will hit resting potential again, and that will maintain until we have another action potential. So that neuron gets used, and then it gets reset by the sodium-potassium pump. So remember, the sodium-potassium pump is what maintains resting potential, but it's also what puts all the ions back where they belong so that this neuron can be used again. There's another term on here, though, that I've said before in the muscle unit, but it also exists in a neuron. So there's something called the refractory period, and the refractory period is a short amount of time after repolarization where those sodium channels stay closed. And what that does, it's very important. What that does is it prevents the impulse from traveling the wrong direction. So you have an action potential occurring at one point in the membrane, and then there's a very short amount of time, it's only like a millisecond long, where those sodium channels stay closed. And that prevents the impulse from going back the wrong direction. So this refractory period is a very short amount of time where those sodium channels cannot open, and that prevents the impulse from traveling the wrong direction. So that's a really important part of this process, and it prevents the backflow of an action potential, and that keeps the impulse traveling from the dendrites to the axon, because as I said before, if the impulse were to go the opposite direction, that would interrupt the flow, and it would essentially cause that neuron to stop functioning. Couple more terms I need to focus on when we're looking at an action potential graph. Here's another diagram, very similar to what you just saw, but there's a new term here. And I'm going to finish up the lecture by talking about this because it's a really important part of this process. So if you take a look here, we have our membrane potential, and you can see at rest it's about -70 here, -60, depending on where you're looking. And then we have our time down here. So let's take a look at this. So the first thing I want you to notice is there's a little addition to the graph here, which I've drawn before, but I haven't really explained. And this is what we're going to focus on right now, which is called the threshold. And the threshold is a term you heard in the muscle unit. The threshold is the minimum amount of stimulation required for a muscle to contract. Well, guess what? The same thing is true for a neuron. There's a minimum amount of stimulation required for a neuron to have an action potential. There's a little window here where the actual neuron can start to depolarize, but if it doesn't get to threshold, it will not have an action potential. So don't worry if that was confusing. I'm going to explain it better. So the first thing I want to point out, though, is before we get into threshold is this idea of hyperpolarization. So we have our action potential, right? We have our resting potential. There's an increase in the amount of sodium that flows into the cell, and eventually enough sodium comes in that we have what's called an action potential. That triggers the sodium channels to open. Sodium floods in, causing it to go up to +30. Then the potassium channels open, causing potassium to flow back in, which brings it all the way back down to -70. But one thing I want you to notice is there's actually a point at which it dips below -70. It actually goes all the way down to about -90, and that is called hyperpolarization. And that occurs because of the fact that those potassium channels don't have two doors. You remember we talked about the difference between sodium channels and potassium channels? Sodium channels have two gates. They have the activation and the inactivation gate. And what that does is it causes a limited amount of sodium to get into the cell, which causes this to spike to a certain point, and then it stops. Potassium, on the other hand, only has one channel. So a lot more potassium is able to get out of the cell than sodium can get in. And what that leads to is a scenario where the cell actually becomes even more negative than normal, and that is called hyperpolarization. And it takes a little bit of time for the sodium-potassium pump to put things back where they belong. So if I go back to my diagram here, during an action potential, sodium floods in. We have our sodium ions coming in. And when that occurs, it becomes just, to use our reference point here, if it's at -70 millivolts, right? So what ends up happening is those sodium come in, causing it to depolarize and goes all the way up to +30 millivolts, right? And then those sodium ions stop coming in because of the fact that we have those inactivation gates. And then the next thing that happens is the potassium channels open and potassium starts to flood out. And it floods out at a high rate, and because those potassium channels stay open longer, it goes down to -70 millivolts, but it actually will go all the way down to -90, and in some instances even lower. And what that is, it's called hyperpolarization. Hyper means more, right? So if this is polarized, this is depolarized, right? Because it's going up, then this would be hyperpolarized. And what that does is it just makes it harder to get back to that, level where we were at. So what that does is it causes this time period where it's not able to fire off, where it's hyperpolarized, and that is that term we talked about, which we call the refractory period. So I just wanted to make sure you understood that. Okay, let's finish up here with our last bit. Okay, and that is going to be this idea of threshold. And I'm going to finish up by talking about threshold. And it's a really important concept, so it's just going to be the last bit of this lecture. So what is threshold? I brought it up when I first brought this graph up on the table here, and I mentioned that there's this little bit of kind of leeway that's given to this situation before an action potential occurs, and that is called threshold. That is the minimum amount of stimulus required for an action potential. So let's talk a little bit more about what's going on there, and I'm going to use that diagram again. Up to this point, I've mentioned the fact that when you look at a neuron, I want you to think of it as being like two separate components, right? We have our cell body over here, and we have our axon over here. And I mentioned the fact that the axon doesn't make any decisions, right? Well, here's where things start to change a little bit. So how do I have an action potential? I don't want my neurons just firing off willy-nilly, right? I want there to be some control to it. So when I have an action potential, what triggers it is this thing called threshold. So what triggers these sodium channels to open up and for the sodium to flood in is that there's this point at which threshold gets reached. So let me just try to explain that as best I can. So at this point we have negative 70 millivolts. This neuron is what is considered resting potential. It is not being used. So how do I trigger an action potential? Well, that is dictated by what's going on down here. So the next part of this unit that I'm going to dive into with you is what's happening down here. How does this neuron get stimulated? But first, I want to finish up with just this idea of threshold because it's extremely important. So there's a threshold which has to be reached, and that is a magic number. It's negative 55 millivolts. That is what this membrane needs to get to in order to have these channels open up and have the sodium flood in. So some sodium will start to accumulate in what is called the axon hillock, and that comes from down here. So I'm not going to explain how this is happening right now because I want to wait to do that. But I do want to let you know that at a certain point what happens is sodium starts to accumulate down here at what's considered the axon hillock. And what that does is it starts to make this membrane here slightly more positive because we're adding more sodiums down here. So what'll end up happening is it'll go from negative 70 to, let's say, negative 65. It is more depolarized, but it still hasn't reached negative 55. So let's say a little more sodium comes in. A little more sodium gets carried into this area. Well, now it's at like negative 60. So we're getting closer, but we're still not there yet. Once there's enough sodium in this axon hillock to hit negative 55 millivolts, that is enough to trigger these voltage-gated channels. So if you remember back to when I started talking about these channels, I said some are voltage-gated and some are ligand-gated. Well, these are voltage-gated, where the outside is going to be more positive and the inside is more negative. Well, when we hit negative 55 millivolts here, what happens is that is enough to trigger these sodium channels to open. So now this sodium channel opens because now the inside is more positive and the outside slightly more negative, and what that does is it triggers these sodium ions to flood in, and then very quickly this number goes from negative 55 and it jumps to positive 30. So think of it like a light switch, like I said before. Until it hits this threshold, until it hits negative 55 millivolts, there is no action potential. But as soon as it hits that positive 30 millivolts, as soon as it hits that negative 55, then an action potential occurs. And at that point, there's no stopping it. It happens here, then it happens here, and that triggers action potentials all the way down the axon to the end of the neuron, and that is what we consider to be a full action potential. So what threshold is, it's the point at which that occurs. So in order for a neuron to actually fire off and have an action potential, it has to first reach that threshold of negative 55 millivolts. If this neuron never reaches that threshold, it's never going to fire off. And what that does is it allows us to control our neurons. Because if they just fired off all the time, well then that would be something like a seizure or, Parkinson's or something where the neurons can't be controlled. But thankfully, we have this threshold in place, and that causes a scenario where it's like almost at negative 55, but not quite there. And then all of a sudden, there's enough sodium in place to cause this action potential. Okay, that's enough for today. We're going to continue on talking about this in class. So if you have any questions, I'll hopefully be able to clear it up there. Thank you very much.